right. All right, well, let's jump in for the last talk of the day. Hopefully we have chosen this properly so that everyone is going to be so tired and asleep, no one will have any objections to anything. Yeah. Okay. So first of all, let me set up a little bit of context on what this work was about. First of all, this was all done at CoreAid in primarily around the 2013 to 2014 timeframe. So this was towards the end of the venture capital phase of CoreAid. And it's kind of an interesting look in the sense that it's what did we think we were looking at for the future 10 years ago? Because this was all in a research setting where we were really trying to ask, what is the future of storage going to look like? The idea was that certainly we do expect to see networked storage the same way we've been seeing it, and we have indeed continued to see that happen. We were wanting to find ways of avoiding, for example, the bottlenecks of the head that you would normally see in a storage environment. And we were also looking at the possibility of blurring the lines between the different types of granularities. And I'll talk about that a little bit more in a minute. But there's different ways you can sort of look at the stuff that's out there to store data on, whether you look at it as files or as blocks or whatever. And so we were wanting to blur those lines and allow for some generality there. Another thing that I wanted to do was to kind of ask the question, is walking really all that necessary? What if we just take the full path name and use that as a hash table lookup to the metadata, rather than having the hierarchical structure that we represent in the names necessarily being reflected in the disk data structures? That was one of the questions I wanted to look at. And finally, and perhaps most importantly, it annoyed me to no end that ZFS came along and called themselves the last word in file systems. Who were they to say they were the last word in file systems? They had used the letter Z. Therefore, I began going through the letters of the Greek alphabet with the plan of ending on Omega FS. As you can see, I got up to theta. So that's kind of a look at where this comes from. Now, it's been sitting somewhat fallow, but in use exclusively in my basement for the past 10 years. And it is also running on this Pi, as we will see. So to talk a little bit about the different kinds of granularities. When we think about a traditional storage device, outside of tapes that is, we're typically thinking in terms of a random access collection of fixed size blocks. And if we present that as the resource over a network, then we get the thing that in the trade is referred to as a storage area network, and a SAN. And this was the type of product that we were producing at CoreAid. Now, the other side of the coin is, okay, maybe I don't want to think of it in terms of the raw block numbers, but I want to think in terms of named things that are of variable size, the things we think of as files. And in that sort of setting, then, if you have the other end of the network talking in terms of files, you have what we will often refer to as NAS, or network attached storage. So it really kind of comes down to a question of where is the break between the management of, if we've got an application here, is the the file system management code and the storage device here is the network between the application and the file system code, or is the network between the file system code and the storage device? This has always kind of been the fundamental distinction between different ways of doing network storage. So around that time, there was a growing interest in a type of storage referred to as object store. It was the up-and-coming thing. The predictions were in 10 years that would be everything. Obviously, the predictions did not come true. But how did the idea of the object store work? Well, the idea here was that instead of having the structure of a file system, instead of having the things like directories and superblocks and all of that kind of thing, you simply have, instead of named resources, you have resources identified by a number or a pair of numbers. And some manufacturers were even beginning to manufacture devices that spoke this. There was basically what they called an OSD, an Object Storage Device Protocol, that was coming into being, where you would always refer to something in terms of this pair of numbers. So that was the trendy direction. And in order to understand where that fit here, I essentially said, well, the reality is our file system is really two parts anyway. We've got our name management here, not MAME, name. And then we've got our storage management here. And so in some sense, what happens is, in an object environment, the network goes right here, between the names and the storage management. And so the thought was, well, really, all of these models are pretty close to the same thing. There's really not that much difference in these models. Why can't we have an appliance which simply is able to talk all three? So that was a big part of the beginning of this system. Now, in order to do that, then I need the protocols to talk them. And so we've got 4 different protocols that are supported by this system. There's, of course, 9P. There wouldn't be much point in talking about it here if it weren't supporting 9P. And of course, that's sort of what we think of as the native one. There's an integrated NFS version 3 server in there as well. Now, at the time, I kind of did a little bit of debating about whether to go version 3 or version 4. But so many of the applications and customers that we had were primarily in environments that only supported version 3 at that time. And there were some things about version 4 that I wasn't sure quite how easy they were going to be to fold into this, that it just seemed to make sense to implement version 3. Though I will point out there are a couple of things about version 4 that are actually a little nicer for us. Version 3 of NFS, of course, is based on the traditional Unix picture of user identification. Integer UID GID. Plan 9's structure is expecting a textual user identification. That means if we're going to do anything with NFS in a Plan 9 world, we've got to have something that maps. Turns out NFS version 4, if I remember correctly, does support textual user IDs. Now, the flip side of all this is NFS tends to expect some things we don't have in Plan 9, like links. Now, theoretically, if you look at the spec for NFS, the links are optional. You don't have to have either hard links or symbolic links. But if you run any kind of system that expects to speak to NFS and do something with that, it's going to expect there to be links. I learned that the hard way. I did not have links. I then mounted this onto a Linux system and started trying to do a big compile and discovered the compiler expects links. So I've got to figure out how am I going to manage links in Plan 9. Interesting question. So these are the two protocols that are being used to access the file level of granularity. Now for the block level of granularity, at Core 8, of course, we had the protocol AOE for ATA over Ethernet. And this gives you an Ethernet frame level description of requests for block access, both reading and writing. That left the question of the object storage protocol. Now, rather than attempting to re-implement SCSI OSD, I added an OSD extension to AOE as an experiment. So the amount of experimentation that has been done in testing with respect to the object aspect of this is very minimal. But it has been used, at least in some basic testing, both as an AOE target and as a file system target, sharing the same storage space. Now, another thing about this that ended up kind of falling out interestingly was I didn't really feel a need at this point to attach a root to the superblock. And part of this evolves out of the idea of I want to use the full path name as the identifier and hash it. As a result, I don't really have to have a starting point that I begin the search from. That means I don't really have to have a root in the traditional sense. This actually makes it easy to have multiple roots. And so you could have multiple file systems sharing the same data space. This is one of the things that ZFS claimed was such a big deal. It's like, yeah, that's easy, yawn. Give me something hard. Now, when you first ream the file system, it creates a unnamed root. So it's designated //. So what happens is, if you have any kind of a name between the slashes, that's the name of the root that you're accessing. And then there's always this one unnamed one there when you first create it. The way that's kept distinct from all of the block access is that each of the metadata entries identifies a type. Basically, I use a quid like in Plan 9, where I've got a path and a type. Block accesses are one type, file and object accesses are the other. Object accesses don't have the prefixing /, file accesses start with the /. So that's how all three hierarchies, or all three granularities, are sharing the same space. All right, so the overall structure, some of it's fairly conventional. There's a super block, nothing terribly surprising there. Because this is doing hashing of the path names, there's a hash table that hashes path names to quids. Now, one of the things that comes up when people talk about this stuff, especially when you get into this world of, oh, hey, let's use objects for everything. There was this debate over whether you should implement objects on an existing file system or whether you should implement a file system on an object store. The former would be fairly simple. You just basically create a directory and name the files by the names of the objects. The latter would be along the lines of, I'm going to create a mapping from file name to object number. Well, Who picks the numbers varies according to which type of mechanism you're using. If I'm living in an object storage world and I'm exporting an object interface, the client gets to pick the numbers. In a file system, I expect the file system to pick the numbers. So for that reason, I have an independent intermediate set of numbers, and those are the quids. So a path gets hashed to a quid. That quid then, there's another hash table that points it to metadata. So the structure of the overall storage space is the superblock, then those two hash tables, then we've got a free bitmap, and then we've got a reserved area for the metadata, very much like the region for inodes in a classic Unix file system, and then we've got our data blocks. Let's see, let me go ahead and illustrate some of this while we're talking about it. So I'm going to, I've got a console device here in serve. Now, I will warn you, I have some regrets about the Greek letters here. And you're going to really love this reason. My file server at home, the console on it is an actual literal VT220 terminal. I don't have the UTF-8 shortcuts on the VT220. One of these days, I will decide how I want to resolve that. Okay, so the command super just prints out the contents of the super block. And it's got the sort of stuff that you expect. It's going to tell us where to find the free space list. It's going to tell us where to find the metadata, where the blocks are. It's got the next number to use for the quid assignments. This stat is going to tell us whether it's dirty or clean, all that kind of good stuff. So this is the sort of thing that you tend to expect for that super block. Now, if I want to look at a path and I want to know what quid corresponds to it, the command p to q is going to give me the path to quid translations. It's going to do the lookup in that hash table. And I'm going to go ahead and use the file that's the slides I'm looking at here. So that would be in papers theta-pres.pdf. And so that tells us that we are looking at quid 2881, which makes sense, considering that the next one to generate is 2882, and I copied this from my other laptop about an hour ago. So I haven't created any new files recently in this file system. Now, if I want to look at the metadata, there's a Q to M that will say, okay, given a quid, tell me which metadata entry has the beginnings of this. And that's where things begin to get a little bit more interesting. Let's see. The metadata, as you can see from this, there's a next pointer in there. Metadata is structured as a linked list. It's not a fixed structure. This gives us the flexibility to add things like symbolic links, or to have some entities that have the AOE major and minor device number, but not have the, say, UID, GID. So the metadata is actually kind of inspired by the extensible metadata in the VMS file system. And so this number that I've shown here, mapping the quid to the metadata, is basically the index into the metadata structures of the starting point, the head of the list. And if I want to look at the entirety of that, this will actually traverse the list and print out all the different values. And so, as you can see here, we've got things like the name of the file, a pointer to a next in the list that has to do basically with siblings. Well, this is our previous sibling. This is our parent. There's our quid path, version, and type, the usual mode, times, size, and the UIDs. Now, this gets us to the data storage part of it. So somewhere in the metadata for this thing, so we've got our path name, papers, theta pres.pdf. Okay, that goes through the path to quid hash table and comes out with a quid number of 2881. That goes into the quid to metadata table, and that points to a metadata list that has a bunch of items in it. And these items are basically tag value pairs. So this is going to feel a little inefficient that we're literally actually doing string comparisons where we would normally just look at a structure member. But again, remember, this is research. I don't claim it to be production. I don't intend it to be production. I use it myself, but that's another story. Now, one of these entries in here is going to tell me where the storage space for this file is. And there are several possible labels that there can be, and dblock is one of those. Now, what I have to do is remind myself now exactly what the different numbers are. So let's go in here. The worst part was I was looking at this last night thinking, okay, I need to remember this. Let's see. Oh no, it wasn't in there that I could find that. These were names, not numbers. So I've got to go into here, and I need to look for dblock. Now, let's see. What's the best way to illustrate this? Yeah, here's a good way to do it. All right. So essentially what happens is we know from typical Unix file systems that you have essentially typically several trees in parallel of different depths. Common way of doing it, you've got an array of direct blocks, then you've got a pointer to an indirect block that points to a bunch of blocks, then you've got another pointer to a double indirect block. Here, everything is always going to be of the same depth. What happens is we will promote it if we need to. So the D block simply indicates a single block that this has. Now, in this particular case, we can get away with that just barely because our block size is 32K. And you notice the size of this file is 32,763, which is, we're 5 bytes away from having to promote this to a bigger representation. And what happens is this. So let's say I've got a D block here. This points to a data block. Now I make the file bigger. I've written 6 more bytes. So what it's going to do is simply allocate another block to become the new root of the tree, make the first entry of the root point to the data, make the metadata item point to the new root, and change the tag to say instead of it being a D block, it's a index. And now we've bumped to the next size of tree. And if we write off the end of that, then we'll do the same thing. We'll just allocate a new block to be the root, change this label down, now indicate we're a tree of depth 2. So that's the way the data blocks are structured in this case. So there's always only one entry in the metadata that points to where to find the data blocks. And the label on it tells you whether this is a data block itself or a tree of what depth. And with 32K blocks, and you can have a depth of 3, as you can imagine, you can get pretty big. That was part of the point of this, was what's the best way to deal with a world in which we're going to expect to be seeing large numbers of terabytes? How do we want to deal with something where we want a single file system to cover petabytes? That was part of the question that we were asking. And so this large block size was actually, it came out of that. The block size, by the way, in some of the earlier experiments was actually 64K. I had forgotten actually at some point that I had dropped it down to 32. I don't even remember exactly why. Now, of course, if you've got a whole bunch of these name value pairs in this metadata, there's likely to be some you don't care about. But that's fine, you just ignore it. So let's say that I'm doing a stat in 9P. Well, I'm just going to look for the metadata items that are going to correspond to what I need to return in the stat message. And I'll just ignore anything else. So if I've got a symbolic link, for example, and we've got a piece of metadata that says this is what this symbolic link maps to, then as far as the 9P view of that file is concerned, it's just an empty file. And that, in fact, is exactly the way symbolic links got implemented. There's a metadata entry called symlink, and its data amount contains the actual path. So let me kind of show you what these metadata items look like. So as I kind of showed here in the bit of code here for it, metadata item has a next, a type, a name, and then this union here. Now, the next obviously is just going to point to the next metadata item for that particular quid. So there's going to be our pointer to the next one. We've got a type here. That, just an enum that defines what the types are. And we've got a name here. So this is the thing like the D block or index or name or whatever. Those are the ones that we see over here in this printout. These labels over here are those textual names that are in the metadata. Now, if the metadata is a string and it's short enough, then we just put the characters of the string right here. If, on the other hand, it's a longer string, then what we do is we put a pointer in here to a place where the string gets stored. And because what we're doing is using an 8-byte value for that, well, if it's a string of length 8 or less, well, actually, because we need to make it null terminated, if it's 7 or less, then we'll just store it in place. Otherwise, we'll allocate it out in some other part of the metadata area and then just plant a pointer to it. For the most general type of metadata, we have a type we call a blob that essentially just says, point out to some bytes. How many of the bytes are there? Here they are. So it can be as general as you want. Now, part of the reason for this generality goes back to the objects again. In the object storage protocols, the protocol defines a set of messages whereby the client can set and request arbitrary metadata values. And so we can't really support objects in that way without having something somewhat, at least a flexible, if not an extensible, metadata representation. So that's where a lot of this comes from. All right, let's see. Now I zipped through a bunch of stuff. I want to see if I missed anything I wanted to say. By the way, I will mention one thing. I almost hate to mention it because I really don't want to highlight the similarity. The VMS file system, like everything else in VMS, was basically the inspiration for Windows NT. So NTFS has a very similar kind of metadata structure. That's the dirty little secret. I refuse to admit to it, however. Yes, that's true. I did make the mistake of saying it in a recording. Okay. We all know that what's on the internet lasts forever, except when you want it to last forever, in which case you can never find it again. Okay, I've already kind of talked about this. This is the mechanism for handling the block mapping. So, kind of a quick summary of the experience with this. Okay, so first off, yes, it did work. I do use it. I have operated it with the same snapshot device that I talked about last year pretty solidly for about 10 years. There was, I will have to tell the story about a little period of time where something went wrong and something wasn't working correctly. I wasn't sure what it was. And I took a first glance thinking, oh, maybe I've run out of space doing the way the snapshots work. And my first glance told me that, no, I hadn't run out of space, there was another problem. And it took me forever to finally get back to coming back and say, okay, let me see if I can figure out what the actual problem is. Turned out the actual problem was I ran out of space. So I bought a bigger SSD, put it in there, added an option to the DevSnap driver to basically resize. And much like the way Venti works, I just copied the first so many blocks, and then the rest of it was where it went. So there is a window in my history that is not recorded because I thought something was wrong that wasn't wrong. Now, was this idea of hashing the paths a good idea? And you notice here I said probably no. I say probably because I want to hedge it. I still think there's a potential that there could be a win in terms of bypassing the walk process. However, 9P doesn't make that easy, and neither does NFS. When you do a walk in 9P, you need to build a list of all the quids that you visited. Well, if you're just hashing going straight to the endpoint, you don't have that. Now, you could, in theory, have metadata that points backwards up the tree, or you could store some other kind of thing. And I've thought about looking at doing that, but I've got to first do some performance measurements to find out whether or not that would be a win. But that's been kind of an annoyance. There's another problem in that I have so far punted on. As you walk, you really should check the permissions of each step along the way. Currently, I don't. since it's only being used by me on my system, I don't really worry that much about permissions. But that's another factor that does need to be brought into play. The other part of the question, though, becomes, is there really anything that depends on that? Any 9P clients that really care about the intermediate quids when they do a walk? And it's not clear that anybody really cares, except for, okay, I can't walk any farther because this name doesn't exist. They frequently want to know where you left off in that process.
How about mounted table?
I'm pretty sure the mount driver takes care of that. I think that that happens before we see it, but I won't swear to that. But that could be a place where it becomes important. Yeah. So that becomes, this was intended to be a next step of the investigation, was really to begin to look into this question of, can we get rid of this tracking of the walk process and just jump straight to the end? Or are the assumptions too deeply embedded? And then the question becomes, is it worth doing that change because of performance? Or is it just really not that bad? Does it really not hurt us that much? So that's one where, in retrospect, I'm not sure we got anywhere. I think there's still potentially something that could be there, but I'm not convinced anymore. I think the structure does work well for providing a unified storage, providing a storage array that will support both block and file, and for that matter, object level access. I think that does work. I'm not happy with all of the integration of it. Having this one monolithic thing that has all of the protocol code in it and all of the storage code in it. Part of the reason for that originally was that because that file system component, depending on whether you're talking 9P or NFS, has different metadata it needs to talk about. I didn't really see a clean way of pulling those out and having a different file system interface here that would allow the file systems to see the devices both in terms of blocks and in terms of metadata. I'm not happy with that part of it. I feel like I should at some point go back and find a good way of doing that so that I can have AOE and the object and NFS as separate drivers or processes even, and then have all of the storage management separate, rather than having one big integrated ball of code. So I'm not real happy with that part of it. But it does work. I have used it for quite some time, not as heavily as I always intend to. It's one of those cases if I get home and go, okay, I need to remember to copy these things over to my file server, and then I don't get around to doing enough of that. But I was using it enough to eventually run out of space on a 64 gig SSD, by which point the cheap ones that were floating around out there were 480 gig. Which gets us back to the classic observation in the early Plan 9 paper. Manufacturers are creating storage faster than we can use it. I resisted believing that for a very, very long time. The more the time has gone by, the more convinced of the wisdom of that observation I am. If you look at most of the space that people use on their system, very little of it is any information they've generated themselves. It's almost always a copy of something else out there on the network. The vast majority of space that you're using is most likely copied from the network. You're just not using up the space for real that fast. And yeah, I ran out of space on a 64 gig device. At that point, you could almost not get 64 gig devices anymore. And the natural thing to buy was, well, almost 8 times as big. When I run out of space in it, well, I may still be around. We'll see. I mean, at the rate I used up the 64, it could be a while. So anyway, as I said, this was really just intended to be a platform for researching these kinds of questions. Not necessarily something useful, but I did feel like it was important to, as the saying goes, eat my own dog food by using the thing that I was working on and to see how useful and feasible it was. And remember, we're still on theta, and I want to get to omega. So there's still several directions I want to go. One of them, of course, is it does make a lot of sense to go to a log structure kind of design. The robustness that you get is really kind of hard to beat in other ways. And I think it makes a lot of sense to do that. As I've kind of already alluded to, this issue of path hashing, I really want to review that. And I've got questions in my mind about it. There are a number of elements that I'm going to kind of lump into the hardening, but I'm going to include things like those permissions checking that happens. That kind of stuff needs to be worked out to make this an actual useful real system. Performance, I have done very little, but a little bit of performance characterization on it. And the most expensive operation is removing things, which again goes back to they're creating storage faster than we're reusing it. So why are we ever removing anything? Okay? I don't care what the business school says. I don't care what the law school says. We shouldn't be removing anything. Just ask the guy who created the FPGA implementation of the Cray 1. He says, well, I've implemented this thing. Now I need some software to run it. Who's got some Cray 1 software? Crickets. They did finally find a pack. Nobody could talk to the drive. There was somebody who figured out some really clever, basically they built their own infrastructure. They had heads that they just recorded the analog signal off the heads and then decoded all that. That seems to be about the only Cray 1 software anybody can find. That's a scary thought. And then, as I said before, I want to split out the networking. I don't really like how it's all lumped together into one big thing. Now, as I've kind of already given away, the slide deck that I'm showing is stored on this file system. I also use this file system to capture some images of the eclipse on Monday. Let's see, I think there were about 800 and some odd images here. I'm not going to show you all of them. I mean, I do theoretically have 15 minutes, but no, actually, I don't have that long. I have 7 minutes. I go through the whole eclipse in 7 minutes. No, I will show you a little bit of something, and let me see if I can remember which. Yeah, okay. Whoops. Does help if I'm actually on my prompt when I start typing. let's see. That's the problem with having the delete key too close to the backspace. These are a few of the images of the limb of the sun as we're approaching totality. Now, this was all just goofing around. Okay, none of this was serious. I don't have really good equipment. Those images were actually a security camera that spoke over Ethernet, pointed at the screen that I was using for eyepiece projection. Okay? No real quality, nothing really all that good there. But I trusted this file system enough to put my Eclipse images on it to record them on there as it was going, given that this is probably the last eclipse I'll see. The next full eclipse, next total in the continental US is not for another 21 years. I don't really expect to be road tripping in my 80s. I'm not promising I won't, but I'm not expecting to. So I have a suspicion this might have been the last total eclipse I'll see. Unless I decide to travel someplace like Australia for one. Those are coming up relatively soon. There will be one in the northern part of Alaska. I think that one's in about 7 years. Yeah. Well, that's true. I'll be up to Omega. All right, so any questions? Yes?
With path hashing, you use the duplication.
The deduplication? Yeah, I'm not attempting to do that. My thought is that, like the snapshotting, what I'd really want to do is make that another layer that this could sit on top of. So that if I want to get deduplication, I can do it that way. Yeah.
Yeah, so I noticed one thing that I thought a lot about when I was putting together GEFS, which I didn't hear anything about in this talk. Do you make an attempt at being crash?
No.
Okay.
Now, what's interesting is that it has successfully survived a number of crashes. You know, it sits there running on my file server all the time, and if we have a power glitch or whatever, then it in fact has done that. But it's never under particularly heavy load when that happens.
And
so
it's running on your snapshot device. You can just roll back.
Exactly. If I had to, I could always go back a day. So I haven't really made any great efforts in that direction. A lot of that I felt is really where I would begin addressing that in the log structuring kind of design. I felt like that would be the place I wanted to really put the effort when it came to the robustness. Yes?
I noticed copyright notices on top of some of those files.
Oh, yes.
I was wondering if there's any plan on releasing this publicly at some point.
Well, these are the 3-clause BSD licenses. So the intent is that anybody can use it.
It's on sources, contrib.
Yeah, I do have it. Now, the version that's on contrib has a couple of things that may get in the way of you trying to actually use it. And I will see what I can do about figuring out. I'm not even sure how to attach to sources anymore.
I thought it was gone.
I mean, I know that the web interface to it on 9p.io is there, but I don't know if you can talk to it with 9p or not.
9PIO, at least on 9front, will connect to it.
That's good.
Yeah.
So
It's in our 9FS.
And now, of course, I have no earthly idea if any of the authentication stuff got ported along. Remember, back in the day, you know, you would go and send a note to Jim or Jeff or somebody, and they would put you in the auth server so that you could get to contrib and you could put stuff in. I have no earthly idea if that's still accessible in any way.
You need to talk to David the Column.
Yeah. But I say that mostly to say that the copy that's on contrib is very close to what I'm running here, but not exactly the same. So if you are interested in trying to do something with it, let me know and I can send you more updated code. I would like this to be treated more as a prototype and as research, and if somebody wants to do something serious with it, take the concepts and the design and implement it from scratch, much like the talk we had earlier about Venti. I'm happy to be the one who does the prototype and leave it to someone else to do the production version.
That sounds reasonable, but are you really sure you want the successor to be implemented in Scratch?
I won't claim any connection to it.
So one other small question. How are you laying out the metadata and other small bits of hash table entries on disk?
So basically what happens is the region that is used for that, I still interact with it in terms of 32K blocks, but I allocate it in smaller units. So the metadata itself, the main metadata structure, as you notice, is a fixed size here. And yeah, it's 32 bytes. And so for all of the items that this sort of works well for, integer values, short strings, and so on, then they're just allocated in 32-byte chunks. For larger chunks, then there's essentially what it boils down to is it sort of rounds up to a multiple of, and then just says, okay, let me grab one of those.
Got it.
So in effect, the free list / free bitmap is just finer grained in those than it is for the data blocks.
Got it. Makes sense.
Yeah.
Have you thought like how systems like Venti fits into this picture? Like
So
instead of hashing paths, you hash the data.
yeah, I did not try to think about integrating it with Venti, partly because again I was sort of thinking in terms of the snapshotting type driver being the replacement for that. Now, I did take inspiration from Venti in the idea of, okay, we're just going to append constantly in the design of that snapshot driver. Could this run on top of Venti? Yes, it could. It wouldn't be too terribly hard. You would pretty much need to have another data structure somewhere that essentially says which blocks have been copied to the Venti and which haven't. And then once a block has been copied to the Venti, you can actually free that block on the local disk, and now you can do your fetches from the Venti. That's more or less what Factotum is doing. And so you could do the same sort of thing here. But I've not really thought about what implications that would have and whether or not it would work well. Yes?
You mentioned the performance, that there are likely performance issues around dealing with paths as strings. Is that something that modern processors with string operations would be useful, or is the context change too much for that to be useful?
I think certainly in terms of the string comparisons for the metadata saying, all right, is this the metadata item I'm looking for? The string comparison part of it, if the compiler is able to detect that and turn it into a single instruction, that's going to ameliorate a lot of that. The structure, however, is still such that you're having to do a linear search through the list and a comparison on each item in the list. Whereas when we have a typical fixed structure like an inode, then you just calculate the offset. In fact, that's done at compile time. and you just add that number to a pointer and take the data. So there's definitely going to be some overhead. And now whether that overhead is noticeable or not, I don't know. That would require a more thorough performance measurements and analysis than I've done. I did have a student one time, I tried to get to do some of that. And unfortunately, this was a case of a student doing a summer research project and preparing a poster at the end. I had not had a chance to completely review his poster. We get to the poster exhibition, and I start looking at it, and I look at the graphs he's got, and I go, wait a minute, something's not right there. That just doesn't make any sense. So basically, I don't have any results from that bit of work. But the little bit of stuff that I did myself, I did things like, all right, let me see what happens comparing, let me mount this using NFS on Linux and do a big compile, and then compare it to something else. That sort of testing was at least ballpark competitive. To be honest, it's been so long I can't remember any more level of detail than that. The only numerical thing I remember from that time frame in terms of performance, so you remember I talked about sort of revisiting the overall structure of the storage network. And I've talked already here about the fact that I'm not real happy about the network and storage being integrated. Well, in the product that we had at the time, there was a similar integration that existed. There was a driver in the kernel called dev-sr. It had the entirety of the AOE protocol implementation and the entirety of the RAID code, all in one driver. And I felt like, the time had come that it should be split apart. And so one of the projects that I did is kind of in this larger context was to do exactly that. Take it and split it into two pieces. The idea being that you could now have things that lived in between the two if necessary. But one of my concerns was, would doing so introduce performance issues? So once I had done that, I was able to, in doing so, I was able to allow for a little bit more general configuration. And so what I did was I configured the storage side to work with a null device. And so I was only testing the protocol part. And I was able to saturate two 10 gigabit links between a Linux host and that server. So I felt like at least that part of it, I was justified in saying, yes, you're not going to lose anything to break those apart, and you're going to gain some flexibility in doing so. Unfortunately, even at the time, I had my doubts about whether it would ever be picked up as part of the product line, and it merely remained part of research. Yes?
So I was running NineAtom until like 3 years ago, and at one point Eric had put this in the tree.
Oh, okay, cool.
And he was very enthusiastic about it. And
He was in the office next to me when I was doing it.
He was encouraging me to try it, and I had a long history of stuff inventing that I didn't want to,
right.
deal with moving over. But my question at the time, which I guess is still relevant, is looking at it sort of the Venti protocol from the other end. If you already have this object store model for it, could you, essentially point fossil at put a Venti interface, server interface on this using the same sort of object store underneath?
I think in principle, yes. I don't know of any particular reason why you couldn't. So if you sort of imagine the hashes as just strings that are names for objects.
Right.
And you use those outside of the root namespace, that is, without any leading slash, you treat it like the names of objects. And you just treat that string as a name. Then in principle, yeah, you could basically make that the object. Now, another way you could do that might be to say, that's probably the best way to do it, because you want to be able to look it up by that name very quickly. And so you really want it to treat it like that's the object number. Now, I'm trying to remember. I'm pretty sure that at least the prototype that I had done for the AOE object protocol would not have supported a number that large. But that would be an easy thing to model. I mean, the experimental OSD layered on top of AOE was just, hey, let me just throw something together and see what works. There wouldn't be anything too terribly difficult about extending that to allow for an object number that could be the hash. And then, yeah, this could then become, that part of it could be the Venti, and then you could also have the file servers. All of it, yeah, again, could be in the same pool of storage. So yes, in principle, it could. It would take a little bit of changes, but it would be doable. Any other questions? All right then. Well, thank you, and we are ending at 3.